Ну вот сегодня у нас доклад. Ярослав, вдруг отчество выскочило ваше.
Анатольевич.
Ярослав Анатольевич Kopylov, вот, автор интересных работ. Значит, вот он, так сказать, диссертант наш недавний. Вот, и вот он расскажет из этого, но у него уже появился, после того, как вас щучили, появился опыт рассказывать, правильно? Ну вот теперь вы нам расскажете то, что сочтете нужным из вашего творчества. Ну вот, слышим. Значит, слушаем вас, пожалуйста.
Прежде всего, спасибо большое за приглашение выступить на семинаре, на этом знаменитом семинаре алгебры в анализе. Это мое второе выступление. Первое было лет 5, наверное, назад, 6 уже.
Ну да.
Да. Ну, наверное, мне стоит говорить по-английски.
Давайте.
Присутствует Мария, еще мой соавтор Миряна должен был подключиться, пока не получилось, видимо, у него это сделать.
Да, нет, у нас есть англоязычные слушатели, так что, пожалуйста. Очень правильно. Вот.
So I will start.
Yes. No,
so the talk will be about Orlicz Cohomology of 2 different types for locally compact groups. This is the joint work with Emiliano Sequeira from Montevideo, but he spent several months in Novosibirsk last year as a postdoc. So, but we had begun while he was there, and we are still continuing to, still finishing this text, this manuscript.
And this is a new.
Yes.
It's after your thesis. Yes, very interesting. Yes.
Yes. So the manuscript is almost over, but we're still polishing it.
Good.
So I think that some of you heard about Pico Homology. So I will give exact definitions a little bit later. So different types of Pico homology have been studied in the last decades. So with different aims. Sometimes with the aim of obtaining so-called quasi-isometry invariants for metric spaces remaining manifolds or so. And or if one speaks of remaining manifolds, the Helder-Poincare inequality for differential forms. So Pico homology was defined for simplicial complexes independently by Goldstein, Kuzminov, Shvedov, by Gromov, by Ehrlich, by Pansu, for Riemannian manifolds, discrete and topological groups, and more general metric measure spaces. I missed Ehrlich in the last line also. So informally speaking, or generally speaking, this construction is a family of topological vector spaces of so-called p-integrable. One considers p-integrable forms or cochains or something like that. And there arises an LP complex. And its cohomology is called LP cohomology. And also the reduced version, so taking the closures of the images, which is better because it's often a Banach space. And the LP cohomology is not separated in general. So about more than 25 years ago, Pierre Pansu introduced Pico homology, asymptotic Pico homology for metric measure spaces. So I will give the definitions in the Orlicz case a little bit later. And he proved that this is a quasi-isometry invariant. And another question we're interested in was we found about 1 year ago, more than 1 year ago already, found a new paper by Marc Bourdon and Bourdon and Remy, who showed that for a locally compact group, a second countable topological group with left-invariant proper metric, proper means that the balls are compact. It's asymptotic and continuous Pico homologies are isomorphic. And so we thought that it turns out sometimes, so this isn't the first attempt to study the Orlicz cohomology of groups. So the first were, I think, there's a paper by Matthias Carrasco-Piaggio, also from Montevideo, but he spent a lot of time in France. and who was one of the supervisors of Emiliano, my co-author. And also Panenko and me considered some problems in Orlicz concerning Orlicz cohomology and Orlicz spaces and topological and discrete groups. And so we thought that it would be interesting, and it turned out to be so, to consider Orlicz space analogs of these cohomologies and obtain, if possible, some Orlicz space versions of the above mentioned quasi-isometry and isomorphism results. Well, it turns out that, of course, Orlicz cohomology is technically harder than LP cohomology, and there is interesting, well, and sometimes difficult problems on the way. So I start with today I'm not going into technicalities, because if we start discussing the proofs, it will be rather lengthy. So I think that I will not go into proofs. So quasi-isometers. If you have two metric spaces, well, it's sometimes convenient to denote the metric as difference, like in linear space. So a quasi-isometer is a function such that distance between the images of 2 points is delayed at most lambda times plus epsilon plus a shift. And also B is sort of subjective. So there is always, for every y, there is always a point x in x, such that f of x is near y. Epsilon must be greater than 0. Sorry, this is a misprint. Greater than or equal to 0. So now we must pass to Orlicz spaces. So I recall the definitions and some basic facts. So we consider the general case when we have a so-called Young function and a negative function, which is even and convex, and is 0 only if and only if t is 0. So, and some facts, well, some facts are true only for n functions. So functions with additional growth conditions like that. Unfortunately, for general Young functions or even for general n functions, Orlicz spaces lack many important properties that the LP spaces have. So a Young function is called doubling if it grows like that. So phi of 2t is at most some constant d of phi of t. Yes, this growth, and it is equivalent that if we, if we take instead of 2, so there is an increasing function of the variable s. I think that I should show it, but it skips all there. Because there's something that doesn't let me show the last line. So phi of st must be at most this d of s, d1 of s.
Вот.
Yes.
Опять закрылось.
I'm sorry, I don't know what to do with that.
Yes, it's impossible to put it up a little bit.
Okay, and all the spaces are considered from basing on Young functions. So if we consider this nonlinear functional rho phi of f, which is the integral phi of f at x of x d mu of x, we use the measure on this on our measure space. So we can consider, as usual, classes of functions. We will say functions f such that this rho phi of f multiplied divided by some constant, this is equivalent, is finite for some constant. And it becomes a linear space with the gauge norm or Luxemburg norm, which is defined in the usual way. And this is the Banach space and is contained in L1 log. So an important feature of Orlicz spaces for doubling functions, is that norm convergence and modular convergence in this functional row phi are equivalent. So in the general case, this isn't so. And the Orlicz space consists of functions for which the functional is finite. And also another important thing is if f is a doubling Young function, X is a proper metric space, which is every closed ball is compact, and mu is a Radon measure, then the space of continuous functions with compact support is dense in the Orlicz space. If f is not doubling, this is not true, even in Rn. So if we have a Young function, we also often is its convex conjugate is considered. This is an analog for p, the conjugate exponent in for LP spaces, p prime. But it's not always Young function. But if phi is an n function, then psi is also an n function. So also there is a general version of Hölder's inequality. We don't need it here, but I will give it for completeness. So which is obtained from Young's inequality. Well, that arises some constant, because if we use the same norm, formally speaking, we must use the so-called conjugate Orlicz norm for the second function. But well, if we use the same norm, then the constant 2 arises. This is because using the same norm is not natural here. So now we pass to the definition of cohomologies. If we have a locally compact second countable group, we consider topological G modules as pairs with these in general Hausdorff locally convex topological vector space over R and a continuous representation P of G on V. Well, so let us consider the space as C gk plus 1v of continuous functions from gk plus 1 to into v with the compact open topology. So it turns out that this is a uniform space. So uniform structure is generated by this entourage. Entourages of this form for the difference, and where U is symmetric convex neighborhood of 0. So this space has uniform convergence topology, which means that the net converges omega S converges to omega if and only if for every compact set K in G, K plus 1, and the symmetric convex neighborhood U of 0, there is a number S, not number, let's use a number S0, such that the difference, the image of this compact set under the difference is in U for every S greater than S0. So, and also this space is Hausdorff locally convex. And G naturally acts in this space by the representation. So one should apply G minus 1 to all arguments, and then apply P of G. And this is continuous. So we will need the subspace of this space consisting of G invariant functions. So the action of G must leave the function intact for every G in G. And this space is denoted usually by adding G as superscript. Well, we will use the construction of a formal differential, formal derivative, which is in all complexes will be constructed by the same model. So if there is any set, no matter what type, and a vector space and subspace in the degree in the power x k to the power k plus 1. The formal derivative is defined for any functions from a to y as the sum of the values of, and we take the set x0, xk, and then from this collection we remove xi, and take the corresponding sign. This is typical for example, if we take simplicial for chains. This model works for many complexes. So we will consider G morphisms, linear continuous mappings between G modules, which respects the action of G. So the following notion I will need only for mentioning that it's used in the proof. So a G morphism is called a strong G injection if it has a continuous right inverse. And a general G invariant linear continuous map between G modules is strong if the induced maps the embedding of the kernel, and this quotient map from the A over the kernel into B are strong G injections. So, and a G module U is called relatively injective if for every strong G injection and every G morphism, there exists a G morphism phi bar such that phi is the composition of phi bar and I. It's a kind of injectivity, categorical injectivity, but with some some specifications. Strong G resolution of this form is called relatively injective is if every module AI is relatively injective. The simplest example, one of important examples, is this complex. So if we take V, then take d-1 as an identical embedding, and then the differentials described above. So we obtain a relatively injective strong G resolution of V. So, and there is a standard fact from the theory of topological modules is due to Guichardet, I think. As if we have a topological G module and two relatively injective strong G resolutions of B, then the invariant complexes, G invariant complexes corresponding to A and B are homotopically equivalent. And if we have an extension of unity of the identity on V between these strong resolutions, then this is topological is isomorphismic cohomology. And so if we have a relatively injective resolution, G resolution of V, then the cohomology and the reduced cohomology of the invariant complex AG are topologically isomorphic to the continuous cohomology of G with coefficients in V and the continuous reduced cohomology respectively. So have I defined cohomology or have I forgotten? So maybe the cohomology is the cohomology of this complex C. I think I missed this, sorry. Sorry, this invariant complex. Or did I say that? One moment. Yes, I must have said it, but maybe this picture skipped. I'm sorry. So let's return to that. So which is cohomology? So one can see that that derivative takes GK plus derivative defined as above, as I did it, GK plus 1V to CGK plus 2V, it is continuous and maps the invariant part into the invariant part. So we obtain a complex of invariant spaces. You see there's a shift in the dimension. So if it's D0 here, from G1 to G2 and so on. And its cohomology is called the continuous cohomology of G with the coefficients in the representation PV. Sometimes P is dropped from the notation when it's clear which representation is being considered. So the cohomology is the kth cohomology of this complex. The reduced cohomology is the quotient of the kernel by the closure of the image. This is Hausdorff. Sorry, I don't know how I skipped this picture because it was of importance. And so I was talking about that computing this cohomology is possible using the relatively injective strong G resolution of V.
Yeah.
Okay. So and then we must define the asymptotic Orlicz cohomology. We can consider metric space. Sometimes we use this notation for the metric, which is sometimes convenient, but not to be confused with the usual metric in Rn. So it must be equipped with a Bourdon measure, satisfying the following bounded geometry condition. There are two increasing functions, V and V and V capital, such that the measure of a ball of radius R lies between the V of R and V capital of R. So the radii of the balls must be bounded. So if we consider the AK plus 1, we can regard its elements as K simplices and define K chains as formal linear combinations of these simplices with coefficients in R. And with the usual boundary operator, D delta, which acts on simplices as follows, on basics, on simplices which form sort of basis here. Sorry. So the delta E D is again calculated as above. Sorry, it misses again. I shouldn't have written on the last line. Well, I did it. Maybe this no. No, it doesn't work like that. Here. So just partial E of delta is the omission of xi. Then x k plus 1 is endowed with the product measure and the distance, which is taken as the maximum of the distances between the coordinates. So for two simplices. Then this product measure also satisfies the bounded geometry condition. So the radii of the balls are bounded from below and from above. And we define subsets xk plus 1 s, which consist of all delta and xk plus 1, whose diameters are at most s. So now if we have a Young function phi, and if we have a Borel function u on xk plus 1, and this number s greater than 0, we can consider the seminorm u phi s as the infimum of alpha, such that the rho fs of f over alpha is at most 1, which is, of course, the usual Orlicz, no, not Orlicz, but we call it Luxembourg norm in but taken on x s k plus 1. So this is the integral. We take this functional and take the gauge normal. This gives the Orlicz space on it. And then consider the global space AS asymptotic AS k phi of x of all measurable functions, for which all these seminomes are finite. So equipped with the topology induced by these seminomes. So another description of this space is, well, first of all, these elements of the space can be, for functions, can be extended to cochains on ck of x. So, and now the description of this space is as follows, as a projective limit. So we, for t at most s, less than s or equal to s, we take the restriction operators. They are, of course, continuous. And we can consider the inverse limit of L phi spaces on this xk plus 1s taken over s. And so this is a Frechet space as an inverse limit from of Banach spaces. But well, the system is dense, in projective system dense in the sense that, well, these mappings are even surjective. You can extend by 0 any form from xk plus 1 t to x plus k plus 1 s. Well, and funny, well, what is funny is that this fact that the limit of Banach space is a Frechet space is stated only for algebras, Banach algebras and Frechet algebras. And well, it was impossible to find the direct reference, so we had to refer to the Banach to Frechet algebra case, because everybody knows that a Frechet space is a countable limit of Banach spaces. But the inverse is not stated directly. Okay, but so again, the topology is generated by the seminomes. And so this is the Orlicz version of the definition given by Pansu for the LP case. So, and yes, as I said, this is the same space as this nomorphism topological vector spaces. And so this space, which we define differently, is a Frechet space. Once again, using the general pattern, which I gave several slides before, the derivative for the coboundary operator is, as it is called here, is defined as follows. And one can prove that it is continuous from ASK phi to ASK plus 1. And of course, to apply it 2 times, the derivative gives, the coboundary operator gives 0. So this is indeed a complex. And it is, it takes several pages to prove that if we have 2 metric measure spaces with bounded geometry and the Young function, then exists, and the x and y are quasi-isometric, then the asymptotic cohomology, which is the cohomology of this complex ASK phi, cohomology are isomorphic is topological vector space, and the reduced cohomologies of this complex ASK phi are isomorphic as Frechet space. So the proof uses the ideas used in the LP case and also some complications caused by the Orlicz space, the nature of Orlicz spaces. So one need to construct a homotopically inverse mapping. Well, it's hard to go into details because either I must expose them all or omit them because there are many. Okay. And the second topic today is is isomorphism between this asymptotic cohomology and continuous Orlicz cohomology. So we consider a locally complex second countable topological group with a Haar measure H, left-invariant Haar measure, and left-invariant proper metric. So, and we have a doubling function phi. And so one can prove that in this case for a phi doubling, unfortunately in this case, so that the right regular representation of G, defined as follows, is well defined and continuous. And we will need the right regular representation for defining the cohomology. So the reduced or non-reduced continuous cohomology of G with coefficients in this representation, right regular representation P phi of G, is called the reduced or non-reduced continuous cohomology of G. So non-reduced this agrees with the definition for an arbitrary representation in a topological module V. This is called continuous cohomology. Okay. And the theorem states that if G is a locally complex second countable topological group with a left-invariant proper metric and phi is a doubling Young function, then the topological vector spaces continuous cohomology, Orlicz cohomology corresponding to phi, and asymptotic cohomology corresponding to phi are isomorphic for every k, and so are the Frechet spaces of reduced cohomology. This theorem is, well, the proof is again rather lengthy, using some ideas applied by Bourdon and Remy for the LP case, and also the specifics of Orlicz spaces. Well, one can show, not very easily, well, that the complex of invariant, which calculates the continuous Orlicz cohomology, is homotopically equivalent to the complex asymptotic of computing asymptotic cohomology. For this, we have to construct, not must, but we have to construct a relatively injective strong G resolution of L phi of G. And it turns out that the associated G invariant complex is homotopically equivalent to this complex. So this resolution is constructed as follows. One considers one must consider one will separate one of the arguments here and skip to one dimension, not to skip but shift by one, and so this must be the space of not some kind of LP space on the group, which is actually LP log with respect to all arguments but one. But this is rather technical and also takes several pages. Okay. Specific and important for applications is the case of degree 1. Case of degree 1. If G is locally complex second countable topological group with its left-invariant Haar measure, G must be equipped with a left-invariant metric satisfying the so-called midpoint condition below, and to have a compact generating set which contains an open neighborhood of either the unity, that is also generated. It's a little bit complicated. So the midpoint condition is that there is a constant such that for any 2 points in X there is a point such that both X minus Z and Y minus Z is at most 1/2 of X minus Y plus C. So this case, if we denote by Z1 phi of G, the kernel of the derivative in the complex of asymptotic homology from AS1 to AS2. Then we can write. So that what is the cohomology here? Because we start from L phi, and the image of the differential coming to Z1 is just L phi. And so this is the quotient of this kernel by dl phi, and the reduced cohomology is the quotient by the closure of dl phi. So in other words, and maybe more clearly, Z1 phi of x is also can be described as the space of functions u in AS1 such that the following holds. Because if you see at the definition of the derivative, it's like that. It has three summands with the corresponding signs. But this is for almost all x, y, and z. So this means that since the left-hand side doesn't depend on z, so one can choose one z, 0, for which this holds. And so we can define a function of x, f u of x, which is u of z, z0x. And then the differential dfu is u, just by contraction. That satisfies this. I have two equalities, three, sorry. So now we consider the space of Dirichlet functions, or phi Dirichlet finite functions. These are functions for which the Luxemburg seminorm rho phi s of f, given below, not given below, but associated with the functional given below, as usual, is finite. This space obviously contains L phi. So we everywhere depend on the set of generators. So one can prove that the differential of d phi of g lies in Z1 phi of g, and also it's continuous, and its kernel is the subspace of almost every constant functions, which is easier than it's continuous. And the induced map of the quotient of d by this constants, by r, into the cocycles is the topological embedding. Also, d is surjective because we showed that dfu is u for every u. Oh, sorry again. And so this is topological isomorphism. And we see that the asymptotic cohomology of G is isomorphic to the quotient as described here of this D or by R, and by the image of L phi arising under the projection of D phi onto D calligraphic phi of G. So this is, well, essentially L phi if the group is non-compact, mu is infinite, something about, well, but anyway. And the same holds for the reduced cohomology. So as we see from what was said above, is phi is doubling, which we are not assuming now, and this quotient is isomorphic to continuous cohomology. Continuous cohomologies, and there's something we don't know now because phi isn't doubling. So we can define the continuous Orlicz cohomology in dimension 1 alternatively as follows. So we can consider continuous functions from G into L phi of G such that the following relation holds. And so-called cocycles. And we take the subspace of those functions that are, as we usually said, the principal or main derivations. And so if we endow that phi of G in the compact open topology, it's easy to see that the mapping of taking the derivative from Z into C1 induces isomorphism in cohomology. Continuous cohomology with this the quotient of Z by B, and the reduced cohomology, the quotient of Z by the closure of the range of G of B phi of G. Well, this equivalence doesn't involve any generating set. So this, whether it's completely generated or not, we don't use it here. But if G does have a couple generating set, which contains an open neighborhood that is also a generator, one can endow Z phi of G with a seminorm, supremum over S in S of the norms of omega of S, Orlicz norms omega of S. Well, but since the modular function of the group is continuous, and this is compact, there is a constant such that norms of PS of F are bounded by this constant times norms of F. And so this and the cocycle condition, omega of GH is equal to P of G omega of H plus omega of G, imply that indeed omega, this norm that we defined, which was a seminorm, is zero, or if and only if omega is zero. And this is a norm, in fact. Thus, the continuous cohomology of Orlicz cohomology of a group is a Banach, reduced cohomology, sorry, is a Banach space. We only knew that for doubling functions, and here it is a general case, but the group has some restrictions as being completely generated, and so more restrictions on the group, but fewer restrictions on the function. Well, now assume that G is a unimodular, locally compact group with a compact generating set, which is symmetric and a neighborhood of 1. Well, consider symmetric generating sets is typical. It's done in the discrete case also for finite generated groups. Well, we also assume that G is equipped with the left-invariant metric, and that its Haar measure is doubling. So, which means that there is a constant, again, for every G and every R, the measure of the radius of double radius is greater than 0, is at most C, the measure of a radius of the ball of radius R. The Young function will be not only doubling, but also strictly convex and function with derivative, having derivative at every point different from 0. And also, yeah, strictly convex already wrote, I'm sorry. Okay, so we define, by analogy with the LP case treated by Tessera and also by the discrete Orlicz case treated by Bourdon and Remy, the phi Laplacian of the function f by the following formula. Of course, this Laplacian depends on the generators, and we say that f is phi harmonic if this Laplacian is 0. Of f is 0 almost everywhere. So if we take an element in the quotient of D by R, by constants, it's phi harmonic if f is a phi harmonic function. It doesn't depend on the representative here, but this definition does depend on the generating set. But, well, as it turns out, there is a one-to-one correspondence between phi harmonic classes of functions for different generating sets. Well, one can prove that delta phi of f is defined for every f and d phi, and it's locally in L1 log. So the main result of this part is as follows. This is an analog what was existed for the LP case and for the Orlicz case in its discrete version. Suppose that phi and its conjugate and functions both are doubling. Then for every element, and the calligraphic G, there is an element in the closure of L phi and the phi harmonic class, such that F is the sum of U and H. This doesn't mean that harmonic functions form a linear a subspace, vector subspace. This set is nonlinear. So you may ask me if there exist functions that are n functions that are doubling and for which the conjugate is doubling, different from the usual t to the power p, to the LP case. Yes, there are some. For example, if you take the function of this form, then, well, it is known to be not, its conjugate are known to be doubling both. Okay. So, and this theorem implies that one can prove from here, it's not hard to prove that classes in the reduced continuous Orlicz cohomology are in one-to-one correspondence with phi harmonic functions. This means that there is a one-to-one correspondence between phi harmonic classes of functions for two different generating sets. So this is, of course, it seems that this is a bad notion depending on generators, but on the other hand, there's a one-to-one correspondence. So again, so you may ask me what happens if phi is not doubling. Well, in this case, there are things that do not fulfill, things that hold for doubling functions, but so it's a little bit hard to explain here, so I will omit it now. Well, I think that's all.
That's.
Yeah, sorry if my talk is a little bit short, but going into details.
Yes.
A little bit.
Okay. Now, so what are questions? So, nobody, yes. It's a difficult but very useful thing, these Orlicz spaces, yes?
Yeah.
Exactly, yes, because they're much more complicated than LP spaces, of course.
Yes.
Yes, and that they are new for many people, but, well, it must be part of our education, I think. They deserve it. So, what are other?
Можно спросить, а в чем, собственно, преимущество?
Это кто? Витя?
Виктор.
Преимущество чего?
Yes, but this is a more subtle invariant, you know. But so, for example, Carrasco considered the so-called Heinze groups, and it is Orlicz cohomology that reflected well the nature of these groups, and not Pico homology. The question, yes, this is a good question. So this is still to be clarified in the future. Which,
thank you.
What objects are described better by Orlicz cohomology? So
yes, and on the other hand, after Orlicz spaces became to be, somehow recognized as true generalization of LP spaces. So a lot of questions concerning LP were asked for Orlicz spaces. So in my opinion, it is quite natural.
Yeah,
so what about
Yes,
what about other questions? Okay. Now, so we indeed have heard a very interesting talk. Yes. So today we stop our activity, and after a week it will be 8th. Denis Vladimirovich Fufayev will give us his talk, and he will send, of course, abstract and everything, and In my opinion, it must be indeed very interesting. So, thank you very much for all people who are present.
Thank you.
And
Mhm.
Thank you very
another
much.
questions or not? No.
No, I just said thank you.
Yeah, yes. Okay.
So I don't know.
So, not farewell, of course. Goodbye.